Today we're going to take a look at section 3.4, which is concavity and the second derivative test. So the first derivative test involved the what? First derivative, right? Yes, it involved the first derivative. What was it finding? I mean, you guys just did a quiz where you're supposed to use it to find something. What is it finding? We use that. We find where it has a slope of 0 to determine what? Extrema. It's all about extrema, right? Well, this test is also about extrema, okay? So it's just using the second derivative to do it instead of the first derivative. So let's take a look first at what the first part of this description called for, which was concavity. Concavity, for a function f that is differentiable in the interval I, the graph is considered to be concave up if the derivative is increasing, and concave down if the derivative is decreasing. So I'm going to draw a graph that you're familiar with, and that you probably would have already told me had we talked about it, was concave up. So this would be considered a concave up graph everywhere. Okay? Let's just look at the right-hand side of it because it's easier to talk about a little bit. If you were to draw slope lines on the right-hand side, right? So we have like this one here and then this one here. The slopes are getting steeper as you move toward the right, correct? That's what number 1 is talking about. It's saying that the slopes are increasing. Hence, the derivative is increasing. Now, it works on the left-hand side, too. It just feels sort of funny because this is steeper, but it's steeper and negative, which means that one compared to this one is an increasing slope as well. It's becoming less negative until you hit the minimum point, and then it's becoming more positive much more quickly as you move on. So this would be a concave up type graph. A concave down graph, we could just flip this one upside down. That would be okay. I'm going to draw something different just so that you can see it doesn't have to actually look like a parabola, because it certainly does not. This graph would be concave down. And it can continue sort of a flattening out feature on the left and continue going downward on the right. And if you take a look and you draw those slope lines, those tangent lines, oops, it's not good. They're decreasing, right? They are becoming more and more negative. Or even if you drew the graph that looked like this one. This one's also concave down, right? It's becoming flatter. It's positive now. The slopes are positive, but they're becoming less positive. So the slopes are decreasing as you go. That's what's meant by the phrase concavity. It has to do with how the slopes are changing. Not what the slope values are, but how they're changing. There is a test for concavity we're going to look at next. Theorem 3.7. If your second derivative exists, so second derivative is simply the derivative of the derivative, on an interval I, and the second derivative is positive, then we say that the graph is concave up. And if the second derivative is negative, then we say that the graph is concave down. So jot those down, and I'm going to go back to the definition from the previous slide and see how these sort of interplay with one another. So according to the definition, it said that it's concave up when it's increasing, right? When the slopes are increasing. Well, how do we decide if something's increasing or decreasing? We take its derivative. That's what section 3.3 was all about, right? How do I find if something's increasing or decreasing? Well, I take its derivative, and I set it equal to 0, and I look at what happens on either side of that set equal to 0 part. Well, what happens when I take the derivative of f prime? Well, I get f double prime, right? And if a graph is increasing, then its derivative is positive. Well, what's the derivative of f prime? Well, f double prime. So f double prime being positive means that I have a graph's f prime that's increasing, which means the graph should be concave up. And likewise for the concave down feature. Now, in reality, this is a much easier condition to check than the previous one. It's a lot easier to determine if something is positive or negative. Right? I just find out what's equal to 0 and I look on either side of it. We've done that before. So that's how we're going to use this information. This is the slide that's going to be most helpful for us in determining concavity. So we're going to do an example. X to the 4th minus 6x squared plus 2x minus or plus 3. And we're supposed to determine whether the graph is concave up, concave down, and the intervals where it is. So I drew some graphs over here that were concave up or concave down everywhere, right? And that can certainly happen, but not all graphs are concave up or concave down everywhere. So let me give you one that's sort of mixed. This graph would be concave down till somewhere about like there on the left-hand side, and it'd be concave up on the right-hand side. So that's what we're going to have the majority of our graphs have happen. Portions of them will be one way and portions of them will be the other. All right, so here's our graph. And it's all about finding the second derivative. If you're asked about concavity, you're finding second derivative information. So let's find the first derivative of this. So somebody help me with that. What is the first derivative here?
4x minus 12x.
Fantastic. And then we're going to do the second derivative, which is better because I don't really want to deal with a cubic that much, do you? Not really. All right, so what's the second derivative going to be? Okay, and then we're going to do much like what we did when we were finding increasing, decreasing. We're going to set this equal to 0, and we're going to set up some sort of a sign chart. Okay? So if I set this equal to 0, and I solve this, I have 12x squared equals to 12, which means x squared equals 1. And what does x equal then? Right. Positive and negative 1. So I'm going to set up a number line, or sign chart, either way you want to think about that. And it's going to have those particular x values on it. So I have negative 1 and I have positive 1. And I'm going to check the values between them. So I need interval values, right? Something between these specific x values. So what might we choose before negative 1? Negative 2 would be fine. How about between? 0 is fantastic. And after? 2. And we're going to test, we're testing for concavity, which means all the information is going to be coming from the second derivative information. So those values, negative 2, 0, and 2 that we just picked, we're testing them in the second derivative to know if graphs are concave up or concave down. So we're going to find out what is y double prime of negative 2, y double prime of 0, and y double prime of 2. And do we care about the value or the sign? The sign. We need to know, is the sign positive or is it negative? So what happens at negative 2? It's a positive. What happens at 0? It's negative. It's negative 12, in fact, right? And then what happens at 2? It's positive. So tell me, what do those positive values tell us about this graph? It's concave up. And what do the negative values tell us? It's concave down. So we found all the information that we need now. So this is concave up where? Negative infinity to negative 1, good. Union 1 to infinity. And you'll notice we're using parentheses still, right? It's increasing, decreasing. It's concave up, concave down on intervals, not at specific values themselves, okay? So this is concave up. And then where is it concave down? Negative 1 to 1. Okay. Did that not really feel like we just did very little different than we've ever done before? We just did it with the second derivative, and it told us information about concavity instead of the first derivative and increasing, decreasing. All right. Now, if in fact the graph does change concavities, that location where it changes concavities has a name. It's called the inflection point. This should say, suppose that f is continuous on the interval AB, and that the graph changes concavity at a point C between A and B, i.e. the graph is concave up on one side of it, concave down on the other side. Then we call the point C, f of C, an inflection point. It's a point where concavity changes. And you can have several inflection points in a graph. You can have no inflection points in a graph. You got all options here. So how do we go about actually finding the inflection points? Well, you kind of already know how to do it. To find an inflection point, you find the second derivative, and you set it equal to 0. And you test to see if the values on either side make it concave up, concave down. And if it changes, it's an inflection point. It also can happen when a value has a second derivative that does not exist at that value. Okay, so like when we were dealing with numerators and denominators, if the denominator gave something that x equal, or if the x value gave the denominator something that didn't work, that's a possibility for an inflection point. All right, we're going to do a little bit of fun stuff on the next one. The directions are, they feel like they're somewhat different than the problem we just did before, but we're finding the inflection point. The process will be much the same. It's just that the answer is going to be that we're finding the inflection point instead of the concavity only. It also says to discuss the concavity, which we'll do that too. You have a couple options. Option number one, you can treat this like a product rule. That's what I actually did in my notes when I created them. Okay. Option number two, we can multiply this all out, and then we can use simple rules. And I'm really not sure which one's necessarily quicker or easier than the other. So you guys tell me what you would like to do. Do you want to treat it as a product rule, or do you want to multiply everything out? Multiply it out? Product rule? Okay. All right, let's do a product rule. Okay, this is a fantastic example of one where it will be very helpful for us to factor things out like you had on your test. Okay, so let's take a look. Product rule says, what am I going to have happen? Okay, so the first piece is going to stay the same, right? Now we need the derivative of x minus 4 to the third. What would that be? Chain rule. So I'm going to bring my 3 down, leave the x minus 4 to what power? To the squared. And friendly enough, what's the derivative of the x minus 4? That's just 1. That's actually very friendly on this particular problem. Okay, but this is only half done. The other half says that I need to simplify the other direction, or take the derivative of the other direction. So I need the derivative of x, which is 1, and then I need the derivative of the, I'm sorry, not the derivative, the original of the second piece, x minus 4 cubed. Okay, everybody good with that? Okay, we're going to clean this up a little bit. You can take a second derivative from this exactly like it is, but it will be easier if we clean it up further. So this is where it's going to feel like what we did on your last test. This one first, I'll just rewrite this. This is 3x times x minus 4 squared plus x minus 4 cubed. Both of these values between the plus sign in the middle have something in common. What do they have in common? X minus 4 and 2 of them, so squared. This is x minus 4 squared. So in the first piece, if I take out the x minus 4 squared, I'm left with 3x. And when I say first piece, I mean this piece right here. All right, the second piece, when I take out x minus 4, what am I left with? Yeah, I'm left with another x and minus 4. Does that look okay? All right, so let's clean that up. I have x minus 4 squared on the first piece. What's the second piece? 4x minus 4. If you'd like, you can factor 4 out of that. I don't know that that's really going to change a lot in terms of our problem, so I'm just going to leave it there for now myself. But you could. All right, so that's my derivative. All simplified, cleaned up, tidy, and everything. Now we're going to do the second derivative, and we notice we have another product rule, right? Okay, so the first piece gets rewritten, x minus 4 squared. What's the derivative of 4x minus 4? 4, right. Plus, now I need the derivative of the other piece, so I'm going to bring my 2 down, the first piece, right, the x minus 4, and it is to the power of 1, if you'd like to write the 1. And then I need to write the original of the second one, the 4 times x minus 4. Okay, and you got a couple options. You could clean this all up by just multiplying everything out, collecting like terms. But keep in mind what our goal is in the end. Our goal in the end is to set this equal to 0 and solve it, right? Well, that means that I need it in factored form, don't I? So if I multiplied everything out, then I'm going to have to factor it anyway when I'm done. So instead of multiplying everything out, I'm going to factor out what they have in common, much like I did on the previous step. What do they have in common? The x minus 4. The first piece now, that is this piece, still has an x minus 4 and a 4 at the end, right? So if you want to write it out, in fact, I think I have enough space, so I think I will just to keep it clear. There's an x minus 4 here, and there's a 4 here still. On the other piece, there's a 2, that is this piece right here. There's a 2 left, and there's a 4x minus 4. And this is kind of where some of you stopped when you were doing your corrections for me on your test. You kind of stopped at this point and thought you were finished. But we need to clean that up because the whole point in having it is to have it completely simplified. So if I clean up what's in that inside of that set of parentheses, I've got 4x at the beginning and I've got 8x at the end. That's 12x. This piece gives me negative 16, and this piece gives me negative 8. So what is that? Negative 24. Doesn't that look nicer? It does to me because our whole point is that we're going to set this equal to 0 to solve, right? So I set this equal to 0. X minus 4 equals 0 gives me that x equals what? 4. What about 12x minus 24 equals 0? What does x equal? 2. Right. Okay, is everybody good so far? So these are places where there are potential inflection points. At least the x value of them, right? Potential ones. We don't know if they are or they aren't, but they're potentially inflection points. The way we decide if they're inflection points is with a number line and testing values around it. So here's my number line. I have 2 and 4, and I need to test values around it. So maybe we test 0, 3, and 5. How's that sound? Where do I plug those numbers into? F double prime, the second derivative, exactly. So I'm finding the second derivative at 0, the second derivative at 3, and the second derivative at 5. And I'm finding out, are they positive or negative? So what do you guys find out? What is F double prime of 0? Sorry, hang on, I'm trying to shift some stuff around to get it more cleaned up. All right, what was it? Positive? Is that what I heard? Positive? Okay. What happened at F double prime of 3? And F double prime of 5? All right, so the concavity does in fact change at those locations, doesn't it? It is positive here, negative here, and positive here. What does positive mean? It means it's concave up. What does negative mean? Concave down, and then another concave up. Right, this is all the information that tells me, which is actually quite a lot. So we can talk about the concavity. That was one of the direction pieces, right? One of the things they told us is that it's concave up where? Negative infinity to 2, and then 4 to infinity, right? It's concave down. Where? 2 to infinity. I'm sorry, not infinity, 2 to 4. And then let's do the inflection points. So we know that we have inflection points at 2 different locations, x equal 2 and x equal 4, but it is a point, and points are written as ordered pairs. Okay, they might ask what is the x value of the inflection point, but if they just say what's the inflection point, they're talking about the ordered pair. How do I find the y value that goes with x equal 2? Plug it into the original. So go back up there, plug that one into the original. What do you have? What is it? 16? And what about, what was it? Negative 16? I don't have this one written down, so you guys don't have to tell me. Negative 16? Are y'all just making things up? Do you know? 2. Yeah, 4 is 0. You're right. 2. Did we really decide this is negative 16? I think it is. Yeah. And 4, 0. Then it wouldn't be an inflection point. Nothing. It could be a max or a min. It could be, yeah. I mean, typically speaking, when there is not an inflection or not a concavity change at where there was a potential inflection point, you have a max or min value, typically. All right. So, second derivative test. That's the last thing in this section. Okay, the first derivative test told us where there were maximum or minimum values using the first derivative, right? Second derivative test is going to do the same thing, but with the second derivative. It's going to tell us where we have maximum or minimum values based on the second derivative. So if you have f prime of x equal to 0, okay, you have critical points, and you test that critical point in the second derivative, that's using the second derivative test. If the critical point in the second derivative is a negative, it's a maximum, and if it's a positive, it's a minimum. And it feels somehow like that's backwards, doesn't it? Negative, maximum, positive, minimum, what's the deal? Well, think about concavity. What does it mean for a second derivative to be negative? How is the graph described? Concave up or concave down? It's concave down. So this right here, this information tells me that it's concave down. Well, what does concave down look like? Well, one way to draw it is an upside down parabola. You see the maximum now? Yeah, same thing. And so the other one then, if a second derivative is positive, this would be concave up. Something like this type of a parabola. And then can you see the minimum? Almost always I visualize this, but every time I do it, I don't actually think about the process or I think about the graph. Second derivative, this means this, and now I've got that kind of a shape going on. So we're going to do, using this, we're going to find out maximum and minimum values. I don't know why there's 2 finds, but just ignore one of them. All right, find all relative extrema. Use the second derivative test where applicable, and there's an A at the end. I think I was tired when I was finally putting all the pieces of this together last night. All right, can we find the derivative of this graph? Sure. All right, so what is the process for this? Well, we need to figure out where those f over here, it talked about things needing to be the critical points, you know, where the derivative equal to 0 business. We have to do that. So here's my graph. We're going to take the derivative using what rule? Quotient rule. So what's the quotient rule say? Okay, denominator, right? So x, and then the derivative of the numerator. What's the derivative of the numerator? 2x minus numerator, x squared plus 1, times the derivative of the denominator, which is 1, over the denominator squared, which is x squared. All right, so if we clean up the numerator, what do we have? X squared minus 1 over x squared. Now we're going to have to do a second derivative in a minute, so that's good to have that down. But right now, we're going to set this equal to 0. So if I set this whole thing equal to 0, I can find that by simply letting the numerator equal 0, right? So if this is equal to 0, then that means that the numerator, x squared minus 1, is equal to 0. So what x values does that give me? Plus or minus 1. I also have to figure out where this does not exist. Okay. Now, for the sake of what we're actually looking at in terms of points of inflection, or in this case relative max and min, that doesn't give me a lot of information, but it does give me information when I'm talking about concavity. So we're just going to have that sort of in our mind as well, because it's going to change my number line if I have to do a number line, that kind of stuff. So if this were to equal does not exist, it'd be the denominator equal to 0, right? So that would be at x equals 0. Alrighty then. We are ready to do the second derivative now. These are going to be my testing points as critical points. What is my second derivative going to equal? the denominator, right? Times the derivative of the numerator. So what's the derivative of my numerator? 2x is correct. Not plus, minus, sorry. Minus the numerator, which was x squared minus 1, times the derivative of the denominator, which is 2x. Fantastic, x to the 4th. Okay, so I need some help to clean up that numerator. This is 2x cubed minus 2x cubed plus 2x. Did I get that right? So what does that become? Yep, 2x over x to the 4th, which reduces to 2 over x cubed. Everybody good with that? Yeah? Okay. We do not need a number line in order to actually test with the second derivative. What does it say we actually do? Well, we found out where the values were equal to 0, this derivative equal to 0, and we need to use those locations where the derivative is equal to 0 and test them inside of the second derivative equation. So my second derivative, f double prime, is now evaluated at the x values I found, which would have been -1, 1, and we don't have to test the does not exist one on this particular graph either, because the directions over here, not directions, but the condition says f prime equal to 0. Yeah, it would be does not exist anyway, right? Yeah, but we don't actually even have to test it. Okay, so what are we looking for here? Signs or numbers? Signs, right? The second derivative test is all about the evaluation of the function and whether it's a sign is positive or negative. So if I plug in the number -1 into the second derivative down there on the very bottom of the screen, what do I get? Positive or negative? Negative. If I plug in +1, what do I get? Positive. Okay, so if it is negative second derivative, is it concave up or concave down? Concave down. Looks something like that. So is it a max or a min? It's a max. If the second derivative is positive, it is concave up, which means we have a minimum. And we can actually write that information down now. We can talk about having, and these are local or relative extrema, so this is a local or relative max at 1 something, was it 1? -1, sorry, -1. And a local min at +1 something. Again, it might be okay, depending on what the problem is set up at, to actually write down just that x equals 1 or -1. If we're asked, however, to give the point itself, how will I find the y-coordinate? Plug into the original. So if I plug in -1 into the original equation, right, the x squared plus 1 over x, what do I get? 2 or -2? -2? And if I plug in +1, what do I get? +2. And I know it feels very awkward because we've now said that our local min has a smaller, our local max has a smaller y value than our local min. That's a little weird, isn't it? But if you can imagine how that could happen, I'm not drawing a picture of this graph, but let me just sort of draw the image yourself. This one would be a local max, this one would be a local min, but could I draw the picture differently so that the, well, you know what, just graph the one you've got. I've already got an equation on here, I don't know why I'm drawing this. Go ahead and graph this original equation. This is a, not a polynomial, which is what I was drawing. I'm going to try and remember what it would look like. I think it looks something like this. Does it look something like that? Am I remembering right? So this is my local minimum, and it is taller, if you will, higher up on the y value than the local max. It's kind of weird. All right, last one, trig one. Let's try to power through this really quickly. Relative extrema, same directions, but I wanted to show you what it looks like with trig. With trig, we still need an interval sort of to stop and start, because otherwise we have infinitely many maxes and mins, so we do have this interval that we're given here. The process starts the same way. We need the derivative. So what is the derivative of a sine of x over 2? I'm missing something still.
1/2.
Yeah, times 1/2, because the derivative of x over 2 would be 1/2. Is everybody okay with that? The derivative of the angle inside is 1/2. We set this equal to 0. Now, the 1/2 at the beginning doesn't affect this equaling 0. So this is the same as the question of where is the cosine itself, cosine of x over 2 equal to 0. So think with me for a moment. My angle is x over 2. We'll get back to that in a minute. But where in the world are the cosine values of a trig function, the cosine values equal to 0? Pi over 2, I think somebody said. Is that what I heard? Is that you, Josh? Pi over 2. Where else? Yeah, and we could keep going, right? Like 5 pi over 2 and 7 pi over 2, and it would continue. We could also use negatives, which would be fine. But the interval that we're looking at is between 0 and 4 pi. Okay? So I don't need the negative side of the graph, and I actually am not even going to need the 5 pi over 2 because my goal is to figure out what x equals, and this has a 2 in the denominator right now, correct? So if I were to multiply everything by 2, I would find out that x is going to equal pi and 3 pi and 5 pi and on and on and on, and 5 pi and on and on and on are outside my interval. There's only 2 locations. All right, we're supposed to do the second derivative, so let's move through this one, get the second derivative down. What is the second derivative? So the derivative of 1/2 cosine of x over 2. Well, what's the derivative of cosine? Negative sign. So here's a negative, and here's my sine, and the angle stays the same, x over 2, right? What number is going to be in between my negative and my sine value? My sine function.
1.
It is 1/4. I already had a 1/2, and I need the derivative of the inside again, which is another 1/2. So I get 1/4. And I need to evaluate this function at the x values that I found in the previous step. So I take my second derivative and I evaluate it at pi. I will take my second derivative and I will evaluate it at 3 pi. So then, what is negative 1/4 sine of pi over 2? Well, what is the sine of pi over 2? It's 1. So this is actually going to be negative 1/4, right? And then I need negative 1/4 times the sine of 3 pi over 2, which would be positive 1/4. All right, negative 1/4 means it's concave down, which means it has a max. Positive 1/4 means it's concave up, which means it is a minimum. So thinking again about writing out what my what this tells me, I have a relative or local max where? Well, it's at pi, right? Wasn't that where I plugged in? X equal pi, and I have a relative min at 3 pi. What is the y coordinate at pi? Back at the original function, sine of pi over 2 would be 1, and the sine of 3 pi over 2 would be negative 1, which definitely fits in with what you remember about trig functions, right? There's no amplitude at the beginning of this one, so it's an amplitude of 1. So it has maximum and minimums at at y equals 1 and negative 1. All right, sound good? Fabulous.